Today we're going to look at stuff that we'll be doing in lab, and we're going to use something called a spectrophotometer. And I'll show you in lab how that looks like. And basically, it has a glass prism that's going to split up light. So for instance, now whenever it rains, you may occasionally see a rainbow. And so what happens with a rainbow? Rainbow is actually this white light. So the light from the sun is this white light. That's all the colors of the rainbow. So white light is the colors of the rainbow. And so you'll see white light. This is what you see for fluorescent bulbs. And what happens is when it hits the rain droplets act like a glass prism, and it splits up the white lights into the colors of the rainbow. And you may have heard that. It's called Roy G. Biv. So these are all the colors that make up white light. So red, orange, yellow, green, blue, indigo, and violet. They all have certain energies associated with it. One thing is that red is about 700 nanometers. So these are nanometers. These are the visible spectrum. And then violet is around 400 nanometers. Couple of things about this one. So lambda is called the wavelength. That's the length of these waves. Let me kind of do this. As the wavelength goes down, the energy goes up. That's important. So stuff around the violet, that's higher energy than the ones at the red. So again, the shorter the wavelength, the higher the energy. Now, we can do this for an individual element. So say I have hydrogen gas. So I just have a tube full of hydrogen gas. I turn on the electricity. So the reason why these things only emit when I put in electricity is that electrons jump. They jump, say I have an electron here, it's going to jump to a higher energy level. And then when it comes down, it emits energy. That's basically how it works. So I have to excite the electrons. So they absorb energy, they jump to a higher energy level. When they come down, they emit energy, and that energy will correspond to a different wavelength of light. So for hydrogen, so when I turn hydrogen on, it's going to give off kind of like a peach color, I guess. It just depends how it looks like. When the electrons drop down, it's going to emit light. Now, we put this in a spectrophotometer, which has a prism. It's going to split up that hydrogen light into the individual colors that make it up. And this is unique for every element. This is how you can identify an element. This is how they identify elements in the universe. They have a spectrophotometer. It emits certain wavelengths of light, and that corresponds to a very particular element. Now for hydrogen, I have one at 410, 424, 466, and then 656. A couple of things with this. The hydrogen, so this is the bottom one, the hydrogen is called a line spectrum because I have lines coming out. So there's gaps in the visible region. This one's continuous because all the colors are in there. So once it's continuous, because all the colors in there, there's no gaps in the visible region. Hydrogen has gaps, and so it's considered a line spectrum. So what we're going to do is we're going to calculate the frequency of 410 nanometers. We want to do it for the line that has the most energy, which is the shortest wavelength. And so a couple of things with that 410 nanometers, I got to convert it to meters, and I'll talk about why in a second. So we're just going to convert it to meters. So again, we've done conversions in class. Basically, when you're doing this, remember, 1 times 10 to the 9th nanometers is 1 meter. And so when I do that, I'm going to end up with 4.10 times 10 to the negative 7 meters. So again, the only thing I did now was convert my nanometers to meters. Now, the reason we had to convert it to meters is that, so this is the frequency. That's the speed of light over wavelength. And again, lambda is that wavelength. Just kind of make sure we get some of these symbols correct. Now, a few things about that when you're doing that is that the speed of light is meters per second. So it's 2.98 times 10 to the 8 meters per second. So the wavelength has to be in meters, so the meters can cancel out. So just kind of be aware of that. You have to convert the nanometers to meters, so your wavelength has to be in meters. And so when I do that, I'm going to end up with 7.31 times 10 to the 14th. And these are inverse seconds. Inverse seconds is just either 1 over seconds or hertz. Those are the inverse seconds. A couple of things with frequency. As the frequency goes up, the energy goes up. So, and again, remember, wavelength was the opposite. Wavelength went down, the energy goes up. So the frequency is a direct relationship. A couple other things, I want to convert this frequency into energies. How much energy is this frequency and this wavelength at 410 nanometers? So to do that, to do this, we're going to use this energy. Trying to see if I can get this to pop up. Okay, so there it is. It's going to be change in energy, that's change in energy between energy levels, is equal to h, which is Planck's constant, times the frequency. And so when you do that, so this is Planck's constant, it's joules times seconds. We multiply by the frequency, which is inverse seconds, so the seconds cancel out, and you're left with joules. And so basically, this is how much energy this wavelength at 410 nanometers has.